top there as usual. We're going to talk about what the universe would look like without quantum mechanics. It's a very short story if you want to make it as short as that. And I'll make it pretty short, almost as short as it can be. We'll go on a little bit. I'll explain what it would look like on the first slide or the second slide, and then I'll uh, elaborate a little bit with the rest. So let's get right into it. Slide 2. What would the universe look like without quantum mechanics? Answer: what universe? Now, there wouldn't be a universe without quantum mechanics for reasons as we'll see. It couldn't exist. We couldn't be here. Nothing could be here if there wasn't quantum mechanics or something like it. I mean, I say quantum mechanics. I always try to distinguish between our models and reality. We don't know what reality is, but quantum mechanics certainly gets one aspect of reality correct, and that is that it moves beyond classical physics, in which we now understand if classical physics were operative, there couldn't be a universe for reasons that we'll see here. Um, Okay, so let's with that provocative. That's by the way, that picture I looked for implosion of the universe was what I was looking for, and this is one of the pictures that showed up. I don't know if that looks like an implosion of the universe or not, but that's kind of what would happen if classical physics were true. Um, the universe would implode in about 10 picoseconds if it could exist at all. You'd have to create it, and then it would implode. Not clear how you'd even create it. So let's go on to slide 3. The history of our understanding of the atom, because this is central to the point. Atoms couldn't exist, and because atoms couldn't exist, the universe couldn't exist. So let's go through our history of understanding of the atom. We had Democritus way back in 450 BC, who just kind of made a philosophical argument that took a lump of clay, cut it in two, cut it in two, cut it in two. He kind of had this idea that at some point you'd get to the smallest indivisible particle of stuff that could be called clay. And if you divided it again, if you even could divide it, it just wouldn't be clay or something. Or however he wanted to think of that. So it's the smallest thing. I'm sure Shamash could take us on a much better journey as to the kind of philosophy of atomism in the Greek days. But I'm not even going to invite him to do it because I've only got 20 more minutes. So okay, and we move on from there. About 2,000 years later, Dalton. Dalton basically understood the idea of elements, that there are a few special kinds of stuff like gold, like hydrogen, etc., which are elements that they are different from other compounds in that there are atoms of those things that have the characteristics that lead to gold and hydrogen. The characteristics of an element are determined by its atoms. Its atoms are identical and uniquely kind of have the qualities of those elements. That was an early entree into our understanding of periodic table, etc. About 30 years later, Faraday discovered that atoms have electrical and magnetic properties. So that's interesting. There's no a priori reason that they should have electrical and magnetic properties, although presumably those properties would come from somewhere. And then a little over 100, well, 125, 120, 130 years ago, Thomson discovered that atoms contain, I shouldn't say discovered maybe, but figured out that atoms contain small negatively charged particles that we call electrons. And so the idea of an atom then became a little more concrete. I mean, a little more structured. That an atom is a neutral thing, but it has these little particles. They were definitely small parts of the atom that we now call electrons, and these things are negatively charged. And the most obvious assumption then is that atoms are is called the plum pudding model of the atom. That the atom is a blob of positive material with little negative specks embedded in it. And people tried to figure out properties of elements based on, I guess by this point we kind of understood how many specks of negative stuff were in atoms of different elements. They tried to figure out how those specs would arrange themselves, how those arrangements might determine the properties. That was a not an ultimately futile exercise, but it was the best they had at the time. And then Rutherford came along just after the turn of the century and discovered that the positive charge and almost all of the mass of an atom is concentrated in a very tiny nucleus, and that the vast majority of the volume of an atom is empty space. So that was an interesting thing, which led finally to Bohr a couple of years later for lots of reasons, proposing that the electrons of an atom orbit that nucleus, and moreover that the energies of those orbits account for the characteristic emission spectra and so on, chemical properties as well, presumably, but especially the emission spectra that are characteristic of different elements. So that's kind of a very quick timeline of our understanding of the atoms. Leaves out.
Whoops, John dropped.
Yeah, I think he left the stage altogether.
Notifications from Clubhouse.
John,
Okay.
you kind of, yeah, you
You
kind of
fell
dropped.
off. Yeah.
Oh, did I drop out?
Yeah,
Oh,
you left the room completely and now came back in.
oh, weird. Am I here now? I don't even see
Yes, you are.
myself now. Okay. I can hear myself. That's weird. I don't know what happened there.
There's a
Okay.
young,
Thank you.
attractive woman instead of you. I don't know who that is, though.
Oh yeah, that's right. That is, in fact, you do know who that is, Sam, because you're the one that alerted me. Sorry, I should have changed my PTR. If anybody's interested in knowing about that, look up "It's Not About the Nail" and watch the video. Sam just
Oh,
hipped me
oh,
to it.
oh, oh, yes, that's the nail lady. All right.
That is the nail lady. Yeah. So look up "It's Not About the Nail" and watch it in a half hour or so when Physics is over, because it's a very amusing. And I think it's supposed to be actually providing a lesson, but I'm not quite sure what the lesson is. So anyway, okay. I'm going to continue on, having very little time here today. We'll move on to slide 4. So what's the problem with all this? Well, the problem with this, with the Bohr, and it really comes up with the Bohr atom, because by the time Bohr proposed his atom, we already knew it couldn't possibly be true because it involved electrons, charged particles, orbiting the nucleus, and charged particles the problem is that stable electron orbits aren't possible because things moving in circular orbits, or any orbit for that matter, accelerate. If they're moving in a circular orbit, their acceleration is the square of their speed divided by their radius, directed toward the center. But the important thing is just that they're accelerating. And two, accelerating charges radiate electromagnetic energy. We'd known this for some time after Maxwell's equations were all put together in the 19th century. So Bohr knew, everybody, physicists knew that accelerating charges radiate electromagnetic energy, and that the radiated power goes as the square of the charge and the square of the acceleration divided by the speed of light cubed and times a constant, which turns out to be 6 gigawatts meters, 6 gigawatt meters per second per coulomb squared. Well, yeah, that may sound like a lot of power, but you have to put those other things in there first to figure out what that equates to. But the point is that the orbiting electron of a Bohr atom, with its charge and its speed, its enormous speed and its small radius, is accelerating fantastically quickly, and therefore radiating power um, at a fantastic rate. Given, the size of an atom, and you don't expect an atom to be able to radiate much power. And because of that, because it radiates all of this energy, it will spiral in just like a satellite orbiting the Earth, which, when losing energy due to drag, spirals in and ultimately decays in the atmosphere of the Earth. Same thing would happen to these electrons. Anything that causes an orbiting object to lose energy has the odd feature of making it speed up. It loses energy because it gets closer and closer to the object that's pulling it in. It's losing its potential energy, but it's also speeding up at the same time. It gains kinetic energy at the same time that it's losing potential energy. That's true with satellites. When satellites decay out of their orbits, they speed up and speed up and speed up, and finally are in such a low orbit that they burn up in the atmosphere, or break up in the atmosphere at least, as they enter it. And that all then proceeds very quickly. Same kind of thing happens with an electron orbiting an atom. So in the case of a hydrogen atom, where you have an orbiting electron with a charge of 1.6 times 10 to the minus 19th coulombs, a velocity that is 1/137th of the speed of light. And that's another really fun story that we may get into sometime. The number 137 is a really important number in physics. And I won't go into that right now. And it has a radius of 5.3 times 10 to the minus 11th meters. That's half an angstrom. An angstrom is 10 to the minus 10th meters. So the radius of this orbiting electron is half of an angstrom. And as a result of that, it will, as I say down there, it will have an acceleration. You can just plug in the numbers to the formula I gave you above. It has an acceleration of 10 billion trillion Gs, 10 to the 23rd meters per second squared, essentially. 9 times 10 to the 22nd is essentially 10 to the 23rd meters per second squared. That is an enormous acceleration. And because of that enormous acceleration, and because of because it's an enormous acceleration, you work out what the power is using the formula that I indicated above. You get 46 nanowatts. Now, that may sound like a small amount of power, and it is on human scale terms, but an atom radiating 46 a single atom radiating 46 nanowatts of power, that's an enormous amount of power for something as small as an atom to be radiating. And so this decay that I'm talking about of the orbit occurs very quickly because that power has to come from somewhere, and it comes from the fact that the atom itself has less and less energy as the electron decays in towards the nucleus. I'll stop for a moment. Any comments?
Maybe very quickly, why is it that a charged particle that is accelerating must be radiating something? Where is that something coming from? From the fact that it's just rotating? Things rotate usually and they don't radiate.
Uh, well, rotating doesn't necessarily radiate unless you have an uneven charge distribution. If a charge distribution changes in general, there will be radiation unless that, for instance, I can have a spherically symmetric amount of positive charge. And if that spherically symmetric positive charge just collapses to a smaller spherically symmetric positive charge, it turns out there's no radiation in that case. But anytime you have a rotating object that is not spherically symmetric, you will have radiation. Why it is, I don't know that I even really want to go there. This is a result of Maxwell's equations. Basically, in simple terms, it's because if you have a certain charge distribution and then you change that charge distribution, the electric field at distance has to change. And it's the process of changing that electric field at a distance that requires electromagnetic radiation. It's the electromagnetic radiation that uh, allows the information of the changed charge distribution at the source to be communicated to a distance. And in the process of changing the electric field at the distance, that really is electromagnetic radiation, variations in the field traveling outward is electromagnetic radiation. I don't know if that helps
So,
a
so
little
if you
bit.
if you imagine a Bohr atom, but that has two electrons that are symmetric, right? And one of them is rotating as the other one rotates. All of this doesn't apply to such an atom, or am I missing something?
Oh, so even in that case, if you have like two electrons orbiting, you're suggesting that one is diametrically opposite the other. Is
Yeah,
that what
yeah,
you're
yeah. That
suggesting?
the traditional
Right.
old, yeah,
Right. And so that would be a case, right? Because at one time you have one electron on top of the atom and one on bottom, and then a quarter of a revolution later you have one on one side of the atom and one on the other side of the atom. Well, that produces a different electric field at a distance. And the process of communicating that different electromagnetic field at a distance is electromagnetic radiation.
I see. All right, cool. Thanks.
Yeah, yeah. No, that's a relatively, hopefully that's satisfactory. We could maybe talk about it in more detail, but I don't want to do that today. Okay, let's move on to slide 5. So I actually did. I actually did. I've seen people talk about this before, but I've never actually done it myself. I put together a little spreadsheet, and if anybody's interested, I should have put a link to the spreadsheet, except that I haven't actually put it online yet. If anybody's interested, get in touch with me. It's a pretty simple spreadsheet, and I simply start with an electron in a circular orbit around a hydrogen atom with a electron in orbit around in the first Bohr orbit, as it's called, the 5.3 times 10 to the minus 11th meters. And I work out this, just what I've done here. Its acceleration, its power, and then I use that power to get a new energy. I let it radiate that power for a tiny amount of time. That tells me that the energy has to be less. I work out from the smaller amount of energy what the new radius and speed of the electron is. And then I work out the power again, let that happen for a tiny amount of time, work out the new energy. In other words, I just kind of watch the energy getting smaller and smaller. This is called numerically solving a differential equation. It's what I always use spreadsheets for. And I get the graph that I show on slide 5 here. This is what I get for the radius of this orbit as a function of time. Now, a couple of qualifications here. This is assuming that there's no relativity. This is a classical world in the sense both of no relativity and no quantum mechanics. So the electron can go arbitrarily fast, and no matter how fast it goes, its energy is given by 1/2 mv squared, the classical formula for kinetic energy. All that stuff is a pretty good in this graph that I'm showing here. That's all not a bad approximation for the first 10 or 12 picoseconds, in fact. So the first 10 or 12 picoseconds of this, it doesn't even matter if relativity is a thing. It's going to look pretty much like this, even with relativity. But relativity is going to kick in last few picoseconds and look a little different, maybe a lot different in some sense. But you're going to get this decay in some form in any event, and you see what you get there. Well, because the because the power is radiated is proportional to the square of the acceleration, and the acceleration itself is proportional to the square of the velocity, and because the acceleration is also inversely proportional to the radius, which is also decreasing. All of those things lead to the fact that the power radiated increases faster than the fourth power of the speed. So as this orbit decays and speeds up, the power radiated increases as great faster than the fourth power of that speed. That means the power radiated increases very quickly. It's enormous to begin with for an atom, and it increases enormously fast. So you see that the radius of the orbit decays relatively slowly at first, right? It takes 10 picoseconds for it to decrease by 20% or something. And then in the last 2 or 3 picoseconds, it completely collapses, and you get the hydrogen atom annihilating itself in about 16 picoseconds. So if you could create the universe it would self-annihilate in 10 to 20 picoseconds, which is why I say the universe wouldn't exist. And just as a side note, I'll point out it's interesting to note that in the first 10 picoseconds, this electron makes something like 10 million orbits of the nucleus. That's more orbits than any artificial satellite has ever made of the Earth. If you launched a satellite back in 1950 and it was still orbiting the Earth, it would only have made maybe 500,000 to a million orbits, I think is what I get at this point. So, in some sense, this decay is very slow, right? Compared to a satellite, orbiting satellite, this decay is pretty slow if you just talk about how many orbits do you have to make in order to decay toward the central object. That's just a little curious side note, I think. Okay, I could stop. I think I'm just gonna finish the last slide, and then we can start the discussion. And when my refrigerator repairman gets here, maybe somebody can take the lead. We'll see how that goes, or we can have an after party later on. So, how did quantum mechanics fix this problem? Benjamin's going to love this because I think it's fair to say that the earliest version of quantum mechanics, the Bohr hydrogen atom, fixed the problem simply by saying, okay, let's suppose it doesn't do that. Let's just suppose that doesn't happen. That's really pretty much what Bohr said. Let's just suppose that for whatever reason, orbiting electrons don't radiate, period. And then let's have a rule that determines which orbits I'm going to allow the electron to have. And that was what he did. The allowed electron orbits, what Bohr said is, let's suppose that the allowed electron orbits are circles in which the electron's angular momentum, its mass times its speed times the radius of its orbit, is an integer multiple of the so-called reduced Planck's constant, which is the normal Planck's constant divided by 2 pi. So he said MVR is equal to n, some integer, times Planck's constant divided by 2 pi. And that Planck's constant was a number that we'd already known from the photoelectric effect and from fixing the Planck radiation law, etc. So that was the rule, and that rule gave you energies for the orbits with differences that corresponded to the spectral lines of the hydrogen atom. It was clearly on to something, but ultimately, it was quantum mechanics. Only certain orbits allowed, and for whatever reason, they don't radiate. So quantum mechanics fixed the problem by just saying, okay, they don't radiate. And that's pretty much true. But a decade later, de Broglie proposed that we can get that same rule in a slightly better way if we make the assumption that the electron can be considered to have wave properties. This was kind of the first rearing of the ugly head of wave particle duality. De Broglie said, what if the electron can be considered to have wave properties, and what if its wavelength is simply Planck's constant divided by its linear momentum? What if that? Because if you make that assumption that the wavelength of an electron is Planck's constant divided by its momentum, then you can recast Bohr's rule for the electron orbits, much like waves on a string, the resonant modes of a string. The allowed orbits are orbits that have circumferences that are integer number of wavelengths of the electron. That was an amazingly appealing idea. This electron is going around the orbit. If, as it goes and it waves, it comes back and superimposes right on itself because it is an integer number of waves in the circumference. The thing shown there, I think, is n equal 3. It goes up, down, up, down, up down as it orbits, and then that's a perfect fit around that orbit. That would be the n equal 3 orbit for a Bohr atom. If that's the case, then it's allowed. Over to the right there is an example of an orbit with a circumference that would have a momentum that would give you a wave that doesn't close on itself. You can see it kind of coming back out of phase with itself, and that's not allowed. So just like resonant modes on a string, you have resonant modes of this electron going around this circle. That was very appealing, but it required this bizarre idea that the electron has wave properties. But with that idea and with the appealing nature of that proposal, it was just a couple of years later, amazingly enough, that all of the work was done that led to Schrodinger's equation, which is kind of the central equation of quantum mechanics. That and a lot of other mathematical details of the quantum mechanical formulation was pretty much finished within a few years after that. And it's a formulation that pretty much survives intact to date. So that's kind of the story of this. But I only give the last page just because I just want to be clear that quantum mechanics really did start just by saying, yeah, let's fix that problem by just saying that for whatever reason, electrons don't radiate. With the wave idea, you can kind of understand it a little bit better because now the electron is not really a particle orbiting. It's just a mushy, wavy thing of charge that doesn't have to radiate because it's not actually changing the configuration of charge. The charge is everywhere in these electron clouds that Sam would tell us about if he were still here to tell us about. That's it. That's all I really have to say today. Sorry for just breezing through it, but maybe that's a good thing. Maybe we can have a little conversation after this, and we'll continue at least until my refrigerator repairman gets here.
Wow, that's exactly half an hour. Well done.
Pretty good, huh? Yeah, I thought it was fun. I just worked out that number of orbits thing. It's just interesting to me that as rapidly as it seems the classical electron would decay in 10 picoseconds, it actually, in some sense, if you think of uh, change in radius per unit time, it's actually kind of, or per unit orbit, per orbit. It's actually kind of decaying in some sense even more slowly than a satellite orbit decays as it enters the atmosphere. Anyway, that's really neither here nor there. So I'll shut up. Les, Benjamin, and Andy, none of you have had anything to say yet. You can say hi if you want, or and I'll invite anybody else down there if you want. Like, I'll read the chat. If anybody wants to come up on stage, raise your hand.
Well, I want to wait for other people to go first because I feel
Oh,
like
okay,
I
that's
too often
humility, I
go
think, is what
first.
Steve Appel would say. I don't know why that's humility, but
Well, as an alpha male, I wanna be a leader here,
yeah.
and
And I don't think
and
anybody ever accused Benjamin of humility. So
and lead other people to go first.
you may have to anyway, but we'll see. Let's see. What
Yeah,
does
well, as
Fred
an
say?
alpha male, I might have to just jump in and show people how it's done.
I think so.
Yeah, I can do this. Either way, as an alpha male, I'm flexible.
We were talking about
Because
alpha
nothing,
males
nothing says I'm an alpha
previously.
male like telling everybody you're an alpha male.
Well, Andy, I think you missed the conversation in Dr. James's room earlier, which I
I
thought
kind
was
of,
pretty fun
I kind
about
of limited
alpha
it, but yeah, yeah.
males. It was pretty good.
I think the term is asshole.
Oh, you were there. That's right. Now I remember because I remember you made that comment.
Yeah. That room was effing hilarious. Okay. Um, yeah, so I mean, the first response is that's kind of cool. Bohr doing that thing that Bohr does, just making up shit. Um, Now, I
Let me
guess
just
you could
actually
say,
let me just say quickly, just call attention. Fred, I think, makes a good comment that 446 nanowatts or whatever, or what did I say? I think that was right. Nanowatts per atom should properly, to really understand how enormous it is. You should really think about having a mole of atoms, a few grams of atoms in front of you, which would be 10 to the 23rd atoms, and then see that rate of power production would correspond to 100 terawatts of power coming out of that little gram of atoms if you did the multiplication. So thanks, Fred. That's a good point. Go ahead,
I mean,
Benjamin.
it could come out, and I guess it does come out in a nuclear event, but
Yeah, it's a very different
it would come
process,
out
though. Yeah,
it would come out very quickly, right? I mean, the energy would be exhausted very quickly. If you
could
got a
be.
terawatt of
Wouldn't have
power
to
out of a
be.
mole,
Yeah.
well, I
I
don't
mean, the
know if
sun the
it,
sun releases nuclear power for 10 billion years, right? So it's
we're talking about a mole, though, right? A mole
right,
of
and
electricity.
every mole in the sun is releasing power at a proportional rate, so
Yeah, yeah.
it doesn't have to release it
Okay.
all at once.
Well, if it was a terawatt, I'm just saying it feels like that the area under the curve's got to be the same either way, right?
Yeah, to release a terawatt, even in nuclear, that would you could only do that for a short amount of time with nuclear.
That's what I was getting at. Yeah.
Yeah, right.
So it is interesting. So there's some challenges I'm thinking of. First of all, you make the first problem. Well, if it's rotating, if the electron is rotating, you call it acceleration. That's fine. Then it's going to release, and it's going to go around. It's going past you to the left for 1 second, and it's going to the right in the other second. And to some extent, these can contradict each other, although it's in orbit, so it's where it's going left is not where it's going right. So there's this differential problem. Maybe you can solve this by making this just bounce back and forth between the two same points, or maybe a complex circuit that bounces back and forth but always returns, backtracks itself, if you will, so that it nulls out all of its own charge, and very probably it is existing in this state. Like if you take light as a propagation of a magnetic field creating an electric field, which creates a magnetic field, all of this is happening. In other words, it's radiating energy, but then it absorbs its same energy, right? And that energy is
There's some
conserved.
problem with antecedents. You say it radiates and then it absorbs. I'm not sure what the it is that you're referring to.
Well, if we take photons in a model, if maybe we accept the model that a photon is, when traveling through space in a straight line, is a series of electric fields that generate a magnetic field, and a magnetic field that is consumed into the process of creating an electric field, which electric field is then consumed into energy. The energy of that electric field is then fully consumed into the making of a magnetic field. And so these two fields are oscillating, and they have really high amount of energy preservation. Um, and maybe something like this is happening when a photon or an electron is captured um, by an atom, but but so it's not progressing through space in the same way. It's just using kind of the atom to kind of circularize that behavior, but
So
it is
let me just say,
efficient
Benjamin, I think
enough.
you're being, I think, kind of unusually, even for you, little. I'm not sure where you're going with this, or what's your thesis here? What are you trying to get to?
Or makes stuff
Um,
up.
no, we just were
Not
enjoying
like
that moment.
Benjamin isn't making stuff up.
I think Ben had a snarky comment or something to say.
No, I
Yeah,
wouldn't
I'll
make a.
take
I wouldn't.
snarky.
I wouldn't make a snarky. I think what Benjamin was doing is showing his incomplete and slightly confused understanding of physics, but using enough technical terms to confuse everybody so that we forget the point. By the time he gets to his assertion, we're all either suicidal or completely confused or both, and we'll never get there. But I'm hoping he will.
That that is kind of my sense
Now,
too, Benjamin. That's
now,
why I was
John,
kind of hoping you could be
John,
a
do
little more
you
specific about what you're saying.
right? Do you see how you talked for like 30 minutes and you couldn't get anybody to respond, and it took me like a minute and a half, and I got half the room
What you mean?
to jump out of their
I should actually
seats?
call this a bite of nonsense, and then I'd get more.
No,
Go.
I don't know if I can
That's a bit
express this
like
without a diagram.
after a good classical concert, everybody might just sit there in quiet contemplation about the good experience that they just had, whereas after a band playing, they might throw tomatoes at the stage. That could be the analogy here.
Yeah, but one of them goes home with tomatoes. The other is empty-handed.
That's true.
So
Um,
aren't you just describing like an antenna? Like if you have a little charge and it wobbles back and forth, it radiates.
yeah,
There's nothing really, I'm talking to John, it's nothing really anything more complicated than that.
Yeah,
Antennas
that's
don't
right.
reabsorb all their own energy or something like that, like Benjamin's suggesting.
but in photons, they do both. They do radiate an
Photons don't
electric
radiate.
field.
Maybe you just misspoke, but
Well, they kind of do, though. The magnetic field
mm,
collapses,
Photons are
and it
radiation. Am I missing
creates
something?
okay.
it creates an electric field, and that electric field is the incremental radiation of the photon. But
Let me just take a moment to say, I mean, I think when I say something like photons don't radiate, I'm instantly these days, I think happily struck with a pang of guilt because, I'm saying something absolutely, which is not a statement about what actually happens in nature. It's something that I don't know and I never will, right? When I say photons don't radiate, what I should always say, but what people should always understand me to be saying when I say anything is that in our model of reality, photons are this thing and they don't radiate.
right, I mean, in the toy model, but I think even in the toy model, as I understand it, at the infinitesimal level, there is a moment where the magnetic field collapses and forms an electric field.
Well, that
It-
has nothing to do with photons. That's the electromagnetic. That's the Maxwell's equations idea of electromagnetic radiation. Photons
Nothing to
don't
do with
really have anything to
photons?
do. But yeah, it really doesn't. I mean, when you talk about
Oh,
photons, you never talk about the electric and magnetic field of a photon. A photon is a quantum of electromagnetic radiation. That's about all you can say there.
well, if
And
we don't agree on that point, then I'm just going to take a break, go on mute, and I'll go find some sources and I'll cite them in the back channel. And hopefully other
okay.
people have comments.
Okay, good. I saw Sam unmute. I don't know if that's because he had something to say. He might have just come in unmuted.
Well, John, can I say I I liked what you said. Okay, so I'd always had this thought of like the Bohr model and like this idea that when people do what you do, just do, which like calculate the decay, that somehow seemed like a silly exercise because like why would you expect this electron to? You're sort of treating this little thing in like a classical sense, but I never heard it so simply put as let's just pretend like it doesn't radiate, and then go from there. But I think that's what I was always thinking. I I like that.
Yeah,
Um, doesn't it also like this is the weird thing, like as bad as the Bohr model is, doesn't it like correctly predict like or at least pretty closely predict like the emission lines of hydrogen or something like that? Like
it gets the important features. It
or
doesn't
it
predict
looks about right or
hyperfine
something. Yeah.
structures and things. There are things related to the fact that electrons have spin that split lines in magnetic fields. So there's lots of details that the Bohr model just doesn't really treat properly. But it is amazing that the Bohr model of the hydrogen atom, as bad as it is, um, gets the fundamentals exactly right. It's pretty amazing.
John, as the alpha male I am, I went and I got that link for you.
Okay.
And if you could just take a second and peel it up, I'll just read it. This is the result of propagation of electromagnetic waves. This is a result of the oscillating charge produced by a changing electric field, which produces a changing magnetic field, and so
Right.
on and so on.
Yeah, yeah.
Right.
I
So
didn't disagree with you on that.
that's the thing we call light. Am I
Right.
missing something? Yeah, yeah, yeah. Okay, okay. We're back on track now. So imagine if somehow the electron existed as kind of the same phenomena where it was oscillating.
Whoa,
Uh,
wait a minute. So now we're talking about the electron being
yeah,
oscillating
yeah.
electric and magnetic fields.
Why can't the electron also um, convert between electric field and magnetic field?
I don't know. I don't even,
With
frankly, I don't even know what that would mean. I'm not sure I even see the model you're proposing.
okay, no worries. I mean, if you can't imagine it, I can't talk you through it, like even in an imaginary way.
Well, yeah, no, I can't. I really, I don't know. Maybe somebody
Look,
else can.
being the alpha male, I'll go see if somebody has written a paper like this, and maybe it just explains it more clearly. And maybe
Yeah,
I'm just making up shit.
I mean, I'm struck right at the beginning. I'm not sure what you thought I disagreed with about this. I said myself, electromagnetic in the Maxwell's equations description of electromagnetic radiation, it's oscillating electric and magnetic fields. And you're right, the changing electric field produces a magnetic field, which changes, and the changing magnetic field creates an electric field, which changes, and they propagate through space as a result of that. But that's not a property of a photon, number one, and it certainly isn't a property of an electron. I don't An electron in quantum field theory is a quantum of the electron field, if you want. But that's not an electromagnetic field, and it's not made
Yeah,
of electromagnetic waves or anything like that.
I think the place where you and I disagree is that it's not a property of a photon. I think that's pretty well established in the toy model. But whether or not it's a property of an
That what
electron,
is a property of a photon?
this propagation, oscillating electromagnetic, electro, and then magnetic, and then electro, and then magnetic propagation is in fact the property of a photon, as I understand it.
Yeah, well, a
But
photon is
whether
a
or not,
quantum of electromagnetic radiation. It's characterized by energy and frequency, if you want, but it's not characterized by electric and magnetic fields. It's a quantum of that electromagnetic radiation. You don't. There's no. There's nothing specific about the electric and magnetic fields of a photon.
well, if one photon is moving through space, then there's one field, electric field, that is converting into a magnetic field, into an electric field,
It's an
etc.
electromagnetic wave. Yeah.
Yeah, yeah. Anyway, let me go see if I can find any support for this notion that electrons might
Okay.
behave this way as well, because I don't think this is a novel idea, even if it's not, even if it's in a
Well, I don't know
heterodox
what is where let's grant you whatever it is you're saying. What's your takeaway from all that?
well, maybe just imagine, if you can imagine a photon or whatever, you don't want to call it a photon, a
Now
light,
we are back to a
a bit of
photon,
light.
not an electron, right? You were saying an
Well,
electron a while ago.
just imagine a bit of light was engaged with an atom in such a way that it was constantly being folded back onto that atom. We could call it an orbit if you want. It could be other things as well. It could be a pendulum, let's say. But it was kind of bound to the atom. But it was a light. In other words, in all other respects, it is engaging in this behavior of going between
It
electromagnetic
being the
field.
electron or this photon that you have, or
Yeah,
what
yeah.
is it? What's the it?
The thing we're calling an electron. That
An electron now. Okay, we're back to an electron. Okay.
Yeah, yeah. I'll go see if I can find. Maybe
Okay.
Hansen can come up and help
Benjamin's
us sort out our
oscillating.
differences. Right. Thank you,
You
Andy.
Uh,
you
what
you
does
are a simple
what
harmonic oscillator.
does
I
what
am an
does
alpha male.
photon folded back onto the atom mean? You
Well, it means
you
that
use that term.
it's
I'm not familiar with it.
well. I think it's easy to. I set this table by describing light traveling in a straight line through space. And now let's imagine that instead of traveling in a straight line through space, it travels in a complicated line that doesn't change its distance from the atom, at least not over time. And so now it's traveling in a strange line. It might be a pendulum like behavior or an orbital like behavior.
Why do I need to imagine this? Where is it going?
Well, because that might be the thing we now call an electron. In other words, there might not be a dime's worth of difference um, between these two. That's
Let me before we go on, let me just say for everybody in the audience, I hope nobody's intimidated by the interactions with Benjamin here. Some of you know we have a long history. Um, the way we treat Benjamin is not the way we treat people in general here. So if you do have good faith questions
You can
or
say it's not the
comments, you're welcome to
way we
come with
treat
them.
normal people. We only treat Benjamin.
And we love Ben, and I also want to emphasize that even though we Benjamin makes us want to scream sometimes, we love Benjamin in our own way. So there's that too.
yeah. I mean, alpha males always get this treatment everywhere they go, and they're used to it. And this is perfectly fine. You're
You know, I
safe
have to
here.
say, I
Mm.
kind of am appreciating witnessing Benjamin's blossoming into his alpha maleness somehow. Like,
Yeah,
I feel
yeah,
like we should have like a cotillion or something.
yeah.
Maybe,
It's
yeah,
good.
maybe a bar mitzvah
It's
of sorts,
it's
an
good to be
alpha
an alpha
mitzvah.
male. Everybody loves an alpha male. I mean, that should be a song.
VP, I've invited you on stage a couple times. I don't know if you're still there. Okay, anyway, there you are. Okay. Let's take a
Yeah,
moment
appreciate
out. Let's take a moment out and go to Joe first, who's new on stage, and then we'll go to VP, and then we'll come back to, the mess that's Benjamin. Sorry, Benjamin.
Oh, I was just joining in case there was some time to poke fun when it came right.
I didn't quite catch that, but did you want to say something now? I'm
He's
offering you
just
the
in
stage.
line to insult me, is what he's saying. He's
Oh,
just
okay.
waiting
No,
his
I
turn.
also curious about the theories that you bring up because, like, a good electron orbital is always fun. I mean, the way that the electron orbitals are organized in the first place, I think so many students aren't even told that the periodic table organizes the electron orbitals. And so half of how they're doing chemistry is hard because they don't even comprehend how the table's organized.
Yeah, okay. All right, thanks. Maybe we'll move on to VP. VP, did you want to make a comment or question or
yeah,
something?
yeah. I was just curious. Like, you ever hear about like child prodigies? Like they're 10 years old and they know how to do like differential equations and physics and all these complicated subjects. And now my question to you guys, because it seems like you guys do all those complicated subjects. So I'm just curious if you had a kid and you had unlimited resources to teach that kid all those, all that science, would you say you can teach a kid who's like 5 by the time he or she is 10 years old, they could have the equivalent amount of understanding and knowledge as the other kid who's 10 who just learned it by himself and has some rare genes that made him capable of learning all that at 10 years old versus
So
just a
I think,
normal kid. Yeah,
yeah.
go ahead.
So I mean, I'll just say, I mean, in my own opinion, I would never do that to a kid. I would never try to generate a 10-year-old child prodigy by cramming math or anything like that. And I do think that there's something special in the brains of, true genius child prodigy types. Um, but I also will say that I think that phenomenon manifests in math way more often than it does in anything else for really obvious reasons, and that is primarily because math is easy in a very important sense. It's just logic and rules. And it's the kind of thing, it doesn't require experience, it doesn't require nuance, it just requires intense, careful, logical thought. And so I think that's why you see so many kids Not so many kids, right? But that's why you do see it when you hear about the most amazing child prodigies. It's almost always math, and then sometimes physics. Although usually physics comes a little bit later. Usually requires somebody with at a slightly higher age. Shamash might have some thoughts on that too, but I certainly wouldn't try to produce a child prodigy. I would, I would, with a kid, I would give certainly expose them to things, show them the fun of math, simple math, take them further if they wanted to. But I think to try to make a child prodigy would be child cruelty in
You know,
some
John, we
sense.
don't have to look that far for a child prodigy because I've spoken with Ben's daughter, and she understands that electricity travels in wires. Clearly, a child
Yeah.
prodigy. So, look,
Okay.
being the alpha male that I am, I've already found the answer to this thing. I imagined it in my head, and sure enough, it's already a theory by Roger Penrose, and it has the best name. It's the best word you're going to hear all day. Um, link is already in the chat because I'm alpha and I rock. But I'll just read the highlighted portion: an alternative perspective of the physical meaning of Zitterbewegung. Did you get that?
Mm-hmm.
Zitterbewegung was provided
Zitterbilligon.
by, yeah, Zitterbewegung. I was trying to explain to you Zitterbewegung. I could have just used that word and everybody would have
I would have
understood
understood immediately. Yeah.
immediately. Because I tried to use words like oscillating light, we got confused, right? So my bad. By observing the Dirac equation can be reformulated by splitting the four-component Dirac spinner into a pair of massless left-handed and right-handed two-component spinners, or zig and
So
zag
you were.
components for
Why didn't you
each.
just say you were talking about spinners in the Dirac equation? We would have all
I
understood what
should
you were
have
talking
said
about, Benjamin.
Zitterbewegung. And next time I will. Next time I will. Next time you will too. Um, because that is a word that has to be remembered. That's the
Yeah.
word of the day.
Well,
That's
I have to tip my hat to you because I don't understand this, and I know that you do. So
I know that I do. Well, look, um, uh, some of this is pretty close to what I was getting at.
yeah, no,
By
I
the
can
way,
see that.
these are. I hope you're tongue in cheek because this shit is crazy. But he is talking, about massless equations moving at the speed of light. I don't know if you can think like of a word for massless. Um, what are they called? Massless whats? Massless? Are they massless?
Assless
He calls
components.
them spinners. Massless components moving at the speed of light. I don't know if you can think of a more colloquial word for massless things
I
moving at the speed of light, but if you
Yes,
think
I
of it,
would.
you just let me
Here,
know.
I can right now.
Joe's got it.
Trembling
Joe
motion.
is my beta.
Okay.
He's going to help me out.
Okay.
Yeah, say
We're
again,
gonna
Joe.
go with the center of gravity between the combination of the Earth and the Moon.
That's what I was thinking. The center of gravity of the Earth and the Moon is a massless component moving at the speed of light. Okay.
Well, I
Okay,
mean,
well,
in
thank
some
you, Benjamin.
cases,
Let's
If I
Fred is
didn't
new on
do anything, a little humor and a brilliant word of the day.
Fred's new on stage. Let's hear from him, and I'm inviting Catmandu up here too. We'll get Jesse on stage.
Oh no,
But
just
go
here
ahead,
to
Fred.
hang
Yeah,
out.
sorry. Go ahead.
Yeah, just here to hang out because I was posting stuff in the chat, so I figured I'd get up on stage too.
Yeah, good. Well, thanks
But
for
yeah,
that
just
thing
saying
about
hi.
the power. That was good. Go ahead.
Yeah, no, it's like 10 times roughly the power grid. That's crazy.
Yeah, but you only get it for 10 picoseconds, so that's the problem.
That's all you need.
That's yeah. No, well, that should be enough, right? If you had that for 10 picoseconds, we wouldn't be here anyway. So, Jesse, Mandu, what have you got?
Yeah, you mentioned yesterday when I brought up about, well, there's something interesting to consider about the type of complex molecular behaviors that happen when neurons communicate using neurotransmitter signals. And you mentioned that Sam would be an interesting fellow to ask about what he thinks about how these interactions are mediated seems to not be quite classical or quantum. So how do we make sense of the complex intricacies of how neurotransmitters regulate signals and metabolic processing and all that good stuff?
Yeah, well, I'm really at sea on all this stuff, and I don't know if that was enough for Sam to feel like he has something to say. I don't even know if Sam is listening now, so we'll see.
I am. I'm listening. I didn't quite get the question. If you could, in a more complete way,
Yeah,
discuss.
yeah, like I think there's some contention with understanding the intricacies of cognitive processing and the lateral dynamics of how clusters of neurons relay neurotransmitter signals in an adaptive fashion, and why it's so resilient compared to like how regular computers function, right? Like how like commercial computers and like how like the how our nervous systems allow us to engage with information as opposed to when we feed commercial computers and quantum computers information, and like the cost of processing that information and how reliable these systems are. Um,
Yeah. I'm also going to punt on this question and say that Wissam is the right person because he's the neurobiologist. I don't understand the mega structures of neurons in the brain, how these clusters kind of organize themselves and how they communicate within the cluster. So unfortunately, I don't know the answer to your question.
and like also more fundamentally, like how like just cells and different organ systems, like just fundamental metabolic processing and just the intricacies of that, and how we can break that down to complex molecule interactions, and how like like subcomponents of the molecules, like parts of the atomic structures that are clustered together for the complex molecules, and the subatomic structures. Like, I don't know if you have any insight into that, like just like how can we think about mesoscale dynamics as opposed to the quantum microscale, infinitesimal scale dynamics and the classical fluid dynamics?
I mean, if you're going to try and do
It's
mesoscale versus atomistic scale, it's still going to be quite a jump. Even
it's
though,
a
I mean, we are talking microns versus atoms, it's
yeah.
still like even just your time domain, right? So on like a mesoscale thing, you can still kind of have um, sort of like a macro scale time frame with certain phenomenon. But when you're talking atomistic stuff, you're talking picoseconds to nanoseconds on the type of behavior, and trying to scale that up to like a mesoscale type of simulation or understanding, it's very, very challenging in the like a grand scheme of application.
So would you put
The
temperature as a mesoscale aspect?
Wait. Let me finish what Cam and Do asked, and then we can engage in other conversations because I still can't answer your question because what you're asking, in essence, is combining a whole bunch of fields. So you asked questions that a physicist asks, an organic chemist asks, and a bioorganic chemist asks, a biochemist asks, a molecular biologist asks, a pharmacologist asks. So your question included all of these fields, and so I don't know where to start answering that question. So if you could kind of narrow your question a little bit more
Yeah.
into at least one area of
I'll,
science, then I can maybe either answer you or tell you where to go look for the answer.
yeah, I'm thinking it might have to do with like the dynamics of like complex chains of polymers, and but I would have to look more into it. Maybe there's some
Yeah. So I
papers
mean,
or stuff that you could uh
yeah, that
recommend.
dynamics that you're talking about can be looked at in two ways. And one is that you look at the biological system as a black box. You say this organic molecule goes in, that organic molecule comes out, and somehow this enzyme catalyzes that process. And you don't really care about that. You just care about what went in and what came out. That's what a biochemist does. But if you're talking about the interaction of complex molecules with smaller molecules, that is, what is the mechanism of that catalysis that goes on inside of the enzyme, then that's a very molecular question that a bioorganic chemist is now going to
Mm,
basically think about. Well, what does the active site of the enzyme looks like? What look like? What kind of transformations are taking place? Things like that. And so, and if you're talking about the structure of the macromolecules, that again goes back to biochemistry that you talk about, like the primary sequences, secondary sequences, the overall structures, and things like
mm.
that. So these are kind of, what the question that you're asking is the question that like a PI on a project would ask. But then the person will have a postdoc who's a biochemist, a postdoc who's a pharmacologist, a postdoc who does this, and then each does their own thing, and then they bring the whole thing back together again. So unfortunately, I can't divide it up that way uh, here.
Yeah, thanks
So
for answering.
yeah, thanks, you guys. I just wanted to address a portion of one question I see in the chat. VV asked something about the decay of the proton, which doesn't have anything specifically to do with what we're talking about here today and the universe existing, but mentions a thing that I think is probably maybe worth pointing out, that in some theories, some of you may know that there are projects looking for proton decay, something that the half-life of a proton is what does VV say? I don't know. Oh, actually, I don't know what it is. I think it's theorized to be like 10 to the 36th years or something like that, which is something like what 10 to the 23rd time, 10 to the 22nd, anyway, 10 to the 22nd times the age of the universe. A trillion, 10 billion trillion times the age of the universe is the half-life of the proton. um, People are looking for it, to see if it decays. And the question was, well, if the half-life is greater than the age of the universe, doesn't that mean it wasn't quite the question, but the implication was, doesn't that mean that it doesn't decay? And the answer there is definitely no. If the half-life of something is, say, 1 million times the age of the universe, and you have a trillion atoms of that thing, then you're going to expect to see one of those things decaying. Yeah, I didn't get the numbers quite right, but yeah, if you have a lot of them, then one of them is going to decay every year or every day or every second, if you have enough of them. So if I had enough protons, I knew the half-life was 10 to the 20th ages of the universe, then I could see one decaying every second, except probably if you work out the numbers, you'd find that you'd have to have more protons than there are in the universe to see that happening. But it's really just that question, the half-life of uranium is more than 1 billion years. But if you have a chunk of uranium and a Geiger counter, you're going to see the Geiger counter goes with dots and Ks every second, just because you have so many um, uranium atoms. So that's just a nice thing to understand. Sorry, little off topic too. But my refrigerator repairman is not here yet, so I'm still here.
Woohoo!
Hey, Shamash, what about that? What about the do you want to say? I don't know if you've ever thought about Democritus's atom, the philosophical, the arguments, the the logical underpinnings of Democritus's argument for atoms. Do you want to say a few words about that by any
Yeah,
chance?
if you guys feel like it. This is a very old problem in philosophy, and every bit of religion, every bit of philosophy has picked up on that question, which is we kind of touched on it in a couple of rooms. If you keep asking why after a certain point, you end up in a very uncomfortable place. If you keep asking for answers and explanations. And what Democritus did is a version of that where he's like, okay, if you just take any body and you start cutting it in half, cutting it in half repeatedly, well, eventually, because you can do this forever, you'd expect that it will become nothing. And that's a very uncomfortable and unsettling realization that because you can always divide it, there's nothing that cannot be divided. And that was troubling for them. And so a part of solving that problem, one way to look at it is to say, well, there's something that cannot be divided. And of course, the other camp would say, well, no, you can't divide it forever. That's no problem. Okay. And all of these are, if you want to call them philosophical thinkings or let's say wet dreams of people who, because today we realize that going down that scale is a very weird and complicated thing to do. And what they had in mind was something very simple, right? So you just cut a piece of paper in half. Well, that's just paper. Cut it in half more, as just paper. And you can imagine that you can do that forever. There's no problem with that. And another version of this, we can see it in Zeno, for example, Zeno's paradoxes, which are kind of also challenging for our intuitions. If you're walking towards a wall, let's say there's a meter, so before covering that meter, you're going to cover half of it. Because before covering half of it, you need to cover the quarter. That's what you do when you step your foot for a meter. You have to cover a quarter and then an eighth and then 1/16. All of these have to happen first. And then Zeno asked, well, how does motion start? So that kind of thinking about the world, again, assuming that it's a real number line and it's completely continuous, etc., it comes with unsettling thought experiments, let's call them.
So
And
Shamash, it
yeah,
strikes me. I sorry to cut you off. I just wanted to, in the case of Democritus, it's all, and I think I've read this somewhere. I mean, one of the key features of his argument had to do with there. I don't know how much it was that there would have to be an indivisible thing, or if it's just that at some point you get to a place where if you divide it in two again, it's no longer paper. And so there's an atom of paper, but you divide it into you still got paper, but at some point there's no paperness left. And so
oof,
in
I
the, I
don't
don't know how
know.
much of it's that and how much of it's really that you simply can't divide this thing. You don't have to not be able to divide the thing again. You really just have to get to a point where it's no longer paper, don't you?
I don't know. I gotta read again. But what I can tell you is this is the analogy he gives. So Democritus was a very professional drunk. Like he enjoyed drinking and having parties, and he was some sort of magician. So uh, we have most of Democritus that survived is a book of magic tricks and party tricks and bets. You know those bets that people do in pubs where you have to remove the paper under the glass to win 10 pounds, etc. That kind of thing is what Democritus did most.
Oh,
And
it sounds
so
like he'd do that. Yeah.
yeah, he's a fun dude. The story goes that he was drinking under the vines during one summer evening, and there were grapes. The vines had to be lifted off the floor, so you can imagine them, like dangling above his head. And he had a wine cup in his hand, and he was drinking. And all of a sudden, he burst saying this. He's like, "Can you see that big grape what do you call it? There's individual grapes, and then there's the big thing that holds them all together. Is there a name for that?
The grapevine.
No, the
No, not the
bunch.
vine,
It's a
but
bunch. Yeah,
It's
yeah.
the
the
bunch.
bunch of grapes. Is that what
Yeah,
you call it?
yeah.
So he's like, if you look at that, you can have individual grape grains, but then those grape grains make the bunch of grapes, and many of those make the vine. Okay, so they're connected with each other, and they make the vine. And then he says, this is how everything is made. So I'm guessing that he
Uh-huh.
reaches a point where you cannot cut more.
Yeah.
That's what I'm guessing. So and
Okay.
this is a fantastic image of, actually, I claim this is what led us to think of matter in the same way. It's that long lasting philosophical tradition, because I don't see any particular reason for us to think about atoms alone. Like, oh, this is an atom, this is indivisible, right? Because it is divisible. We know now that electrons are
Right.
part of the atom. We know that protons are, but because that
The name
philosophical,
atom no
yeah,
longer means the most smallest indivisible part. Yeah.
but then this is what we call matter. Anything that is below that, we just don't respect it somehow. You know what I mean? And so it's that unsettling philosophical problem of, where do things come from, and how do you make things up, and they had no idea, of course. And so I'm guessing the answer to your question, John, is that you get to a point where you cannot divide anymore. But I have to read again to make sure.
Okay. So Mary, I don't know, Mary Yule, Godcads, joined us on stage. I don't think I've ever met you before, but correct me if I'm wrong and correct my pronunciation of your name. And what would you like to say?
Oh no, I just wanted to come and listen in on the conversation. I thought it was interesting. Yeah, you're right. This is the first time I'm here.
How do you say your name?
Oh, it's gonna be difficult for you to pronounce it, but it's Meriola.
Ah, okay, Mariola. How about
Yeah,
that?
close enough. Yeah, that's
Close
actually
enough.
pretty good.
Okay. All right. Well, thanks. Good. Welcome. Speak, unmute if
So
you want. I kind of pay attention to unmutes, and Sam has unmuted, and now he has the stage.
thank you. I'm the alpha guy who just inserts himself into everything without regard to. Anyway, so Shamash and John. So now that we know genetics, and now that we know quantum mechanics, are those Zeno paradoxes? Are those Democritus's thought experiments? Do they still make sense? Because I mean, Zeno's paradox of the most famous one of them, the cut the distance in half, you're going to run into the quantized state of matter that you can't,
Well,
you
I've
know.
never found Zeno's paradox compelling in the least. Yes, I get that you have to go 1/16 of the way before you can go 1/8 of the way, but you do it in 1/16 of the time. And you have to go 1/32 of the way, and you do that in 1/32 of the time. There's no, uh, it may be a pre-calculus puzzle. People who have not had
Yeah,
calculus,
but
I
that's not the
imagine.
point, John. The point is
Well, okay,
he's
so I
looking for the
don't
starting
understand
point.
the point.
You know what I mean? He's looking for the first
No.
step. Every process has to start with the first step. And if you
Yeah, I
follow that
still don't
logic,
get
there
it.
is no first step. That's the unsettling bit.
I guess I've never been unsettled. Maybe I'm just not bright
Because
enough
you're
to get it,
imagining
but
it
I don't.
as an infinite sum on like about 1/2 plus 1/4 plus 1/16. And
But
then
don't you?
that's not what it is. It's three dots and then plus 1/8 plus 1/4 plus 1/2 plus 1. That's what it is. It doesn't
Well,
begin with the first term.
maybe I guess it just strikes me as
But
pre-calculus
what's the
confusion.
point of it, right? I mean,
Mhm.
the thing is that instead of saying, I mean, besides going, gee whiz, that's neat. What else are you going to say
Okay,
for
so
Zeno's
let me tell this
paradox?
story. So the most badass of them all is Diogenes the Cynic. He's the number one biggest maniac of all of those Greeks, and I can talk for hours about Diogenes because I love the guy. But
Don't
to
do
add
that, Shamash.
for,
Hey, have
for
you
Sam's
have
point,
you have you read Cloud Cuckoo Land
no,
by it's by Antonius Diogenes?
no, I have never heard of the book. Is it like a
Okay,
book about Diogenes or
uh,
something?
actually, it's a book. by someone else. It's a modern book, but talks about a kind of a book that is missing a whole bunch of pages by Antonios Diogenes, and it's a really good book. I read it. Anyway, go ahead.
All
Go
right.
ahead.
So Diogenes heard Zeno lecturing because Zeno was a kind of a big guy. You know, he was part of this bigger circle called the Epicureans, and they were fighting the Aristotle people and the Plato people, etc. So he heard Zeno lecturing, and Diogenes hated all of these philosophers, as you say, Sam. It's like, what's the point of all of this? And so he walks in, and as Zeno was explaining a version of his paradox to his students, he looks at Zeno, and then Zeno looks at him back, and he stops talking, and he starts walking in front of him. He's like, "Step one, step two, step three.
Yeah,
There
that's
you
what
go.
I
I
do.
can walk. What's your problem?" Right?
Yeah, that's
And
exactly.
yes, in some
I
sense, I
like this
understand. Yeah.
Diogenes guy. He's my kind of guy.
But then but then I can do that too, but I don't have an answer to
To
to to
how?
to give to Zeno. I don't, and it's not only me. You can read Bertrand Russell's commentary on this, and he called it the greatest logic puzzle ever, or one of the greatest logic puzzles. It's
Wow,
like
Bertrand
it's
Russell
difficult.
even.
Yes, it's
Well,
very
how
difficult to answer.
about we just say baby steps? Baby steps, man. Baby steps.
Well,
Well,
I think we're running into, the age-old dichotomy between an experimental scientist and a philosopher, right? That the philosopher says blah blah blah, and then the experimental scientist says, so how's that going to change my experiment? Like what we were talking about in the previous room with Alfonso, and he always brings up, do we have free will? Do we have this? And I'm like, it doesn't really matter, because you make your decisions and you go on and you live your life. It doesn't really matter if you're making this decision of a free will or preordained or whatever, right? Just do whatever the hell you're doing, because it's not going to change anything if you have free will or you don't have free will. You're still going to make the same decisions. And these types of philosophical arguments that Zeno brings up about, oh, this is a paradox. I'm like, okay, yeah, it's an interesting puzzle, but is it going to change the way we do science? Is it going to change the way we think about our world? Is it going to change the way I'm going to make lunch today? No, it's not going to do anything, right? So it's just there.
Well said, Sam. And ultimately, the title of the room resolves this anyway, because I've been busy talking to other people, so I presume you're talking about the convergence of an arithmetic progression, that type of thing, the whole going half as much
Zeno's
distance as you went.
paradox, more generally. Yeah.
Yeah, I don't know
Yeah,
it by name. I
that
don't
that
know it by name,
progression.
but is
Yes.
that where you kind of go half as much distance as
Yes.
you went before, and then you quote never
Yes.
stop? I mean, well, you do stop because you get down to the granularity of nature. But apart from the fact that
You
even
you
in a
get to the
smooth,
quantum state, and so you can't cut
yeah,
it anymore, and then you're done.
I
You
mean,
reached
apart
it.
from the fact that mathematically it does converge, and that's interesting, and yeah,
I
But
I think
if space wasn't quantized, do we think Zeno's paradox would really be a real thing then? I mean,
It's not the
I
I
don't.
point.
sorry.
You're
Yeah,
missing the
sorry.
point.
If I could
I
It
interject,
know
doesn't
I
so
kind
actually
of
I
am.
bother.
think
It doesn't bother me whether it is or isn't quantized.
Yeah,
Zeno's
I don't
paradox
think
isn't a
it doesn't
paradox
bother
because
me either.
yeah.
the
So
progression converges. I mean, who cares?
yeah,
So
because yeah,
Marioli,
if I could
It's
interject.
Mariota,
just
yeah.
limits. It's just understanding limits, right?
Yeah, if I could interject, I think Zeno's paradox has very, very little to do with conversion and limits, and if anything, it has more to do with, I guess, what philosophers in the 20th century would refer to as super tasks. The question is not whether or not the distances add up to a finite value, or whether the amount of time spent is meant to add up to a finite value. I think the issue really is the way Zeno phrased it. You can phrase it in two different ways, and I think Shamash, the way you're phrasing it, is sort of the reverse version of the paradox. But if you're supposed to put it in its sort of strongest form, it goes as follows, right? You have, as you know, you have an infinite number of halfway distances, and each distance can be marked by an individual point, at least hypothetically speaking. and you're going to have to cross each point one by one by one. The question isn't whether or not the overall distance adds up to a finite value. Rather, it's how can you progress going one by one to the point where you reach an infinite quote unquote step, right? Because there seems to, without I guess jumping over points, because if you go 1, 2, 3, 4, 5, 6, there's no number such that the next number is going to be an infinite number. There's a sort of gap between the finite number scheme and, or I guess the natural numbers, and these sort of I don't know, transfinite numbers, whatever you want to refer to them as. And that seems to be what the issue is. The issue doesn't seem to be whether or not you can do this in a finite amount of time, or whether the distance is actually finite, or whether the distances actually add up. It's how do you cross these points one, 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 such that all of a sudden you're at the next step is an infinite step.
I
Because
think.
this. Go ahead.
Sorry, go ahead. Well, let me just say. I mean, I think what you're saying. I mean, I can tell from the way you're saying it, from what Shamash is saying, that you're right. That my understanding and dismissal of Zeno's paradox reflects my lack of understanding of it. And I think what you're saying is the point. But I still don't get it.
I
I
can.
don't
Well,
understand
yeah, I
what
still
the
I
don't
think. Hold on.
problem
I
is.
think
how is
before we
that
get
going to
off that
change
point,
anything?
before we get
Can
off
I
that
make it
point,
a
though,
point?
I think what I think what Mary Pohl is talking about is the difference between countably and uncountably infinite numbers. And if you're constantly halving, you can do a
Yeah.
Cantor diagonalization, right? You can put all of the fractions on the horizontal and vertical axis of a grid, and you can enumerate that grid by counting diagonally. It's Cantor diagonalization. It shows that that's a countably infinite set of numbers. I think that's different to the real numbers, for example, which are clearly uncountably infinite. So I think I think that is a valid way of looking at it, and that is the borderline between the mathematics and the reality. But it's a countably infinite series. Is that what you're trying to get to, Mary?
No, this has nothing to do with countability or uncountability, right? I think it more has to do with the fact that this is a process in which you're, I guess, engaging in successive addition. And, it's not even successive addition, to be honest. It's more like you're counting ordinally, and then suddenly you have to go from, I guess, a finite ordinal position to an infinite ordinal position, which shouldn't be possible in theory, seeing that before the infinite ordinals, there is no direct, I guess, uh, predecessor that's a finite ordinal, if that makes any sense.
I think
Not
it's
not
just
really.
this is like a
Uh,
weird personal choice though. When you make a statement of like, well, to cross a distance, I got to go half the distance, and then I got to go half the next. Like that's a weird decision, a weird way to characterize the problem. Like I
but
could
at the
equally say I could go half the distance, and then I can go the other half of the distance, and then I'm
And
done.
it bears
Um,
ultimately always on time, right? I mean, I think the only way to be, I find that the only way I can be puzzled by it is if I somehow allow myself to think that there's just all this time that's going to be taken to do all these things. And it just isn't. That just
No,
doesn't bother me at all.
I think in real life space is quantized. I mean, in the Zeno's paradox, space is quantized, and the lowest quantum state is the length of your foot, because you're never
But
going to cut your foot in half to go half the
but
distance.
but you
But then, wait, Juvin has been patiently waiting to chime in.
Thank
Yes.
So
you.
welcome
Thank
to
you,
the
Sam.
stage, Juvin.
Let's do hear from Jubin. Yeah, go ahead.
Yeah. Hello. Thank you. Thank you. Just with regard to Zeno, what Zeno was trying to say was you can't have your cake and eat it too. If you think the
Well,
space
now I
is
know I'm sorry, Jubin, to interrupt, but I just want to say now I know I don't like him. Go ahead.
yeah. No, if you think he says if you think the space is continuous and infinitely divisible, therefore you cannot start moving. And that geometric progression you mentioned, the sum of it is if you start with one, you start two or half, is one minus one over two to power n, which is n is the number of divisions. And the small thing is important to him. So when we say we start moving towards the wall 10 meters away, and we go half, one quarter, and one eighth. Suppose there is an epsilon distance in front of you, and you want to go forward one epsilon. Then you got a half that, half that, half that, and that 1/2 to power n. So it's not exactly 1 or 2 whatever. So therefore you can't start the motion, and that's what he's trying to say. Therefore everything is mental. If you That's why he says you can't have your cake and eat it too. If you want to think the space is continuous and therefore everything is mental. All the motion you see and everything is mental. Therefore then he's so clever as well. Then he assumed that the space is made of chunks, and I forgot the details of it. He puts like cubes next to each other and says these are pieces of space, and there are like 4 or 5 of them are moving from left to right, and 4 or 5 of them moving from left to, and he finds a paradox there as well. If you go and search that, he actually finds a beautiful paradox there as well. Just another point, John, with regard to Democritus, that logic mentioned, he does answer that when the paper is not paper. But once they postulated
Mm,
that everything is made of indivisible particles, they also said the way these particles arrange themselves, they become water, they become
mm.
stone, they become things and whatever. So they postulated that, and also the person who
So
came
hold
after.
just a quick second. But the idea would be that the particle, the atoms themselves are all identical, but there's kind of a smallest grouping of them that's paper. Is that what you're saying?
What they said is the way these indivisible particles, the way they arrange themselves, then they make, like we have come up with the notion of atom and molecules and whatever. So they said, obviously they didn't know. They said, they postulated that the way they arrange themselves differently, they become different substances, like water,
Hmm.
like stone, like brick, and whatever.
Right.
And the person who came after him, I forgot his name, Logic should know, that carried on that idea. He actually produced something like uncertainty. That he said, when these particles fall into our earth or whatever, they come. He came up with the idea that for their position and the moment or whatever, similar
Well,
idea, but not exactly
that
like
would
that.
be
Very
surprising.
clever. If you Logic should don't know the name of the person who came after him, continued the atomic. Uh,
Is it
po- po-
Anastasius? Is it that's what you're referring to?
Sorry, who's that?
Anastasius?
No, 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 no. After democracy, he carried on, the idea, and he added quite, few things. If you search that, you can find out, very clever.
Hmm.
But
I
Trying to
do.
find that.
I do think I shouldn't have brought up the quantum thing, the whole idea that quantum resolves it in the real world. The Zeno's paradox is a mathematical world. It's nothing to do with the real world. And even in that mathematical world, the reason it sounds like a paradox and it isn't is because because the difference between the countable number of steps you take and the uncountable number of points that you pass through. In a single step, if space is in the mathematical space we're talking about, aside from anything to do with physical reality, there's an uncountable number of points in a single step. So we're dealing with the difference between the countable number of steps and the uncountable number of points you pass through in taking those steps. And because it tries to confuse those two, that's what sends our brain into a spin. When you separate those two, it becomes very clear, in my opinion.
Ben,
well,
I don't
if
think.
you yeah, see
Go ahead, Julie.
what you say. See, if you think that space is continuous, made of infinite points, that's why you hit this paradox, that you won't be able even to move one epsilon in front of you, because you got to go through those half and half and half. But
That's the
that,
part I just can't wrap my mind around. I don't understand why it makes any difference whether space
Yeah,
is
I
absolutely
continuous or
don't
anything to
not.
think
do
the
with how space
notion.
actually is. The mathematical paradox isn't a paradox. It's just mixing countable and uncountable infinite series together in the same
Yeah.
I don't
But
think
so
the
particles.
How's
notion of
let
real
countability?
numbers had
How's
been
how does
developed by then,
countability
right?
solve?
Like,
Sorry.
let's hear
Because
from
in a
let's hear yeah, let's hear from Andy too. He's
well,
trying to get in.
I was gonna say, I don't think they had the notion of real numbers yet, right? At this point, so they
No, no,
didn't.
no. They had no idea.
So I guess in that world where all you have are integers and ratios, maybe this kind of thinking makes sense. But you can have a continuous world and you can have motion. You just need to take calculus. But that took a while. I think this is like a proof by contradiction. Like if you have a system and you come up with an absurd result, then there's something wrong with your system. Um, there's something wrong with your words or your logic. So like to sit around and keep arguing about it, it seems like the silliest shit in the world. Obviously things
We've
move.
we've
So what? It's so weird to me that people would continue to consider this clever.
But it is to the extent I'm willing to believe that Bertrand Russell called it what I think Shamash said he called it, right? A serious thing, and that means something to me that he said that. But I still don't get it. It's just all. And we have so so one comment. It's interesting to me that and it's okay. We've turned this into Philosophy Wednesdays. We should probably do an advertisement for Philosophy Wednesdays for everybody's here
On
and
a
still
Friday.
interested in listening on Friday. That's right. Shamash does do, if you don't know, if you're not aware, he does a Philosophy Wednesdays, same time as this room is on Wednesdays. And it's fascinating. I find it fascinating. I think some people find it less
Yeah.
fascinating. Some people
Uh,
find it more fascinating. So you
you
should
should
do that.
also know that whatever we're discussing here is infinitely more comprehensible than the chemistry room yesterday. So
Oh, Sam, you didn't have to say that. Sam does chemistry
But
rooms too, and they're good, especially good if you're not waiting for refrigerator repairmen and not
Sam, you
paying
need to be a
attention
little
like I
more
was.
precise, though. Is it countably or uncountably infinitely more confusing than the chemistry rooms?
Yeah,
it's
and we're joined by
uncountably, it's infinite.
we have Mr. G. Gelvani, who I don't think I've met either on the stage. So I'd like to make a little room for him. And so what? Yeah, welcome.
Here, good afternoon. Yeah, Steve, I talked to you before in your other rooms, the room that was
What
about
you go
religion.
by, Mr. G?
Yeah,
Okay, go
you
ahead.
can do both. Either one you are comfortable. Actually, my question is that how far we are so far to measure the time and space.
Can you be a little more specific? I'm not sure what you're getting at.
Well, when you go down for measuring the time and space.
Oh, you mean in terms of quantized space and time? Is
Yes,
that what you're
yes,
thinking?
quantize, yeah,
Yeah, I don't think
quantize.
there's any good evidence that time and space are quantized, although a lot of people do and have theories of gravity and kind of quantized relativity. I don't know much about that. So, but there's no good evidence, I would say, other than the fact that you can combine some physical constants and get a time out of it and a unit of space out of it that are smaller than anything we've ever been able to measure. And that's kind of that's provocative enough to make you think that maybe these things that you get just by combining physical constants that give you a time that's really small or a space that's really small, you might think, oh, maybe that's a quantum of time or space. And it might be. And people will try to make things out of that, but there's no evidence, I would say, that that's true.
To
By,
really,
academically, as far as I remember, I read about it in a scientific article that so far they were able to measure 10 to the power of minus 18.
per
This
second.
is
Well, that
one
seems a little
time.
small, I think, for the
Yeah. Then
time.
yeah, they right now they are able to
Oh,
measure
oh, I see what you're
to
saying.
10 to the
Right. I think that's about the smallest time interval that can be measured, but it's
yeah,
still enormously larger than the thing that people suggest might be a quantum of time.
yeah. So when you are talking about quantum, it
Right.
all just go with the time and space. And yeah, I had my other question as when the time becomes zero, what do you think about that?
Well, what do you mean by the time becomes zero? You mean if the
You know,
quantum of time was zero, or you mean back at the beginning of the universe, or
when the
what
time
do you,
stops. When the time
sorry,
stops,
when time started,
stop.
He means
stops.
interval of time zero.
Yeah, is that what you mean? What if the quantum of time was zero? Or I mean, I'm still not quite sure what you mean.
Yeah, when the time stops. In very simple word, when is the time stopping?
I don't know. Maybe does somebody else understand? I'm not sure I understand what
When
you're
when you when
asking.
you're asking when does time stop, do you have in mind a universal clock that has everything running? Is this what you're imagining?
Yeah, I don't know. I'm
Well,
asking this. I don't
because
know.
because because
But
if this is the meaning of your question, then I can immediately tell you that physics doesn't understand this. This is not something that has any meaningful repercussions, because the way physicists define time is very particular to every system or every particle. Every one of us
well,
has their own clock, and so it depends on how fast you're moving relative to other things. So I can't
well,
really answer the question when does time stop, because you're going to have to tell me what is it that is measuring it. So for example, for a photon, time always is stopping because its clock never moves,
In
but
some
for
sense,
us
they
we can
don't
see
have
it
a
coming.
clock. Yeah.
Yeah, exactly.
Yeah.
well,
Yeah.
when it's coming to binary, on and off, 0, 1, just that iota, iota of time, it come to the
Yeah.
point that it has to come to the point that the zero become one, and it has to come to the point, a stopping point, that one becomes zero. So just as an example, 0, 1, 0, 1, 0, 1, constantly it's becoming to one point, it comes zero, to be able to switch from 0 to 1. That is
Well,
when, this is my idea, that is when the com becomes zero. If it
But
doesn't
time is
become
not
zero,
binary.
I'm sorry.
Time is not binary. Time is not 0, 1, 0, 1. I mean,
yeah. I just,
Okay,
I confess, I don't
yeah.
even begin to understand what you're
I
getting at. Sorry.
okay. When you are talking about, there are, in order to process information, you are using the bit, but they use the binary, trinary, and all these. From the binary, at the time that the zero become one, one becomes zero. This all
See,
takes
I mean,
time.
already zero become one, one becomes zero. What are you talking about? I have no
So
idea. Really,
I
literally,
say,
no idea what
yeah.
you're talking about.
I know you don't get. I'm sorry. I
Yeah,
know it.
no,
You
I'm
need to
sorry
think
too.
about it.
Yeah, I would like
I
to, but I'm
I thought
afraid we're
about
not
it.
going to.
I
Sorry, go ahead,
I
Sam.
thought about it. That's why I
Oh,
say,
no, no, I
it
have.
is hard.
okay.
It is hard to understand. But
Yeah, no,
when
I'm
the zero
sorry.
becomes one,
I'm sorry, Mr. G. I think unless you can reformulate it some way, unless there's anybody on stage who has even the vaguest idea what Mr. G is talking about, I think we'll have to move on.
so I'm
Well,
trying to explain it. I say
Yeah.
how much time it takes that zero become one. How much time it takes?
in
Okay. Well,
infinity, it
Uh,
never happens.
yeah. I
The,
think we'll
I
I
think
think
it's gonna
I'm sorry,
it's
Mr.
gonna
G. I think
consider.
we're gonna move on. There's a couple more people on stage waiting, so I'm gonna move on
Okay,
to
okay,
Solon.
okay.
Yeah, I'm sorry. That's just the way it is. The Solon first, and then Poseidon.
Yeah, so I have a question. So when we say, like, from the perspective of photon, no time has passed for photon. So is it something that is arbitrarily we have fixed and said that that is the speed limit? Um,
So,
so
mm,
what I mean
yeah.
by that is that if there is something that is moves faster than a photon, then would we fix this new thing that is faster than light as something that no time has passed?
Well, so I mean, all we're really doing is when we talk about the photon in no time, is just basically taking the Lorentz transformation seriously. As an object moves closer and closer and closer to the speed of light, we would say that its clocks are running slower and slower and slower. Um, and it takes and we would see it. For instance, if I saw something go from here to Alpha Centauri at very close to the speed of light, I would see its clocks say that the people on board only aged by 3 seconds, let's say. That's a rocket that's moving very fast across a distance that I say is 4 light years. And yet their clocks only advanced by 3 seconds. They would say, oh, it only took me 3 seconds to get here. And of course, they would also say that it wasn't 4 light years. Just wasn't that far. I got here in 3 seconds because it wasn't very far to Alpha Centauri. And if they were traveling at the speed of light, if they were literally traveling at the speed of light, then the Lorentz transformations suggest that their clocks would not advance at all. They would get from here to Alpha Centauri in zero time, according to them, according to their own clocks. And they would say that's because here and Alpha Centauri are the same place. There's no distance to travel from here to Alpha Centauri because they are literally at the same place. So, a photon, if you take the Lorentz transformation seriously, something traveling at the speed of light doesn't even experience time. All places along its path are the same place as far as it's concerned. And if you continue to take it seriously and you have something traveling faster than the speed of light, then we would see the clocks on that thing moving backwards in time, meaning in some sense that, traveling faster than light is in some sense traveling the other way in space or time. Not clear what that means. And so, but people take the idea of what they're called tachyons seriously. Tachyons would be particles that travel faster than the speed of light. They have very odd properties. Their energy gets less and less. Less and less the faster they go. To slow down to the speed of light takes infinite energy. To travel infinitely fast takes no energy for a tachyon. So there's all sorts of weird properties if you take the Lorentz transformation seriously. And history kind of shows that if the math of physics says something is possible, then you ought to take it seriously. It must mean, sorry, it must mean something. Excuse me. Sorry, bit of a coughing fit. Somebody else take over for a moment.
Hi, can I ask the question?
Sure, of course. Go ahead.
Okay, I think I'm going to ask multiple questions if possible. The first question is on the collapse of the wave function on Copenhagen interpretation. Um, I think the wave function is a real physical entity, not just a probability. And
You
do you
think
think,
that?
what's that?
You think that?
Yes, and also on the gravitation,
That
quantum
makes you the
gravitation.
only one.
What's that?
That makes
Well,
you the
not
only
quite the only
person who
one.
thinks the wave function is an actual physical entity, because even
It must,
Schrodinger said
yeah, it must,
that he is proposing the wave function as a model, not as an explanation of what the physics of it looks like.
and the second question is, I think on the collapse of the wave function, if we don't know the gravitational effect, and we call it as collapse of the wave function, and if we somehow find the gravitational effect on the quantum physics, then it won't be a collapse of the wave function anymore. That gravitational loop quantum gravity will determine the wave function at the end. It's not actually the collapse. What do you think on this question?
Yeah, I
Oh,
don't
look,
often weigh in on things like that just because, well, for two reasons. Number one, I like to keep these rooms on more well-established physics. You're getting into speculative physics. That's a good thing. People should speculate, figure out things, try to see if there's experiments we can do to see if those speculations have some validity.
Actually, it was also
Um,
Roger Penrose's interpretation.
Yeah, Roger Penrose has some bizarre interpretations. Some of which I think, I mean, personally, I think I kind of like. Some I don't. I think he's gotten a little crazier as he's gotten older. He used to be my candidate for the brightest physicist of the time. He really isn't. But this is just my opinion. I'm just weighing in on my opinion about the things he says, and that doesn't matter.
I'll weigh in because somehow I feel like I was called on.
Go ahead. Go ahead, Ben.
You're in the right place. If you follow half the people on the stage, you'll end up arguing about quantum every other day, and that's exactly what you want to do. So you should follow us. None of us are going to agree with you. That in no way, shape, or form disqualifies you from the arguing club. So yeah, jump in. Loop quantum gravity. Uh,
Yeah, because
but
on my take on like physics and cosmology and loop quantum gravity, often considered a little bit on the what you call the crazy side. So I often tend to be
but
on the quiet side.
So
that's quite all right. That's quite all right. John Mallinckrodt believes in multiple universes, and there's no
Can I
less crazy.
weigh in a little bit here? So I think if you go through the right introductory textbooks on like learning kind of like from the surface of like what the heck is going on with like why is quantum mechanics interesting, right? This idea of a wave function is to capture a measurement on the subatomic level. Normally electron behavior is pretty much what a lot of these textbooks like they play with like the electron model. um, and the idea is we want to measure the momentum or position of displacement, but we can't capture both. So this is why we consider the wave function to be associated with the uncertainty principle, right? Because we can't be certain about the position and the momentum regarding the displacement
Okay,
simultaneously, right?
let me stop it. Let me stop it here. Sorry, because a lot of things that got mixed up here that shouldn't
I
get
was
mixed
going to
up.
say a little slide serving
So
of EPR word salad there.
so when people came up with the theory of quantum mechanics, the question was, well, how do we express this? How do we work with it? How do we mathematically move it around? And so Heisenberg came up with the matrix algebra system, that his matrix algebra could basically express what they were calling quantum states, and and be able to mathematically manipulate them. About a year after that, people realized that physicists are not as good a mathematician as Heisenberg thought, and they're not comfortable with matrix algebra. And so Schrodinger came and said, all right, I'm going to take the matrix algebra of Heisenberg and I'm going to express it in terms of waves because physicists understand waves. They know all the equations about waves. And so I will explain quantum phenomena in terms of wave functions. This doesn't mean that quantum phenomena are waves. It just means that in our incomplete science, where we don't have sufficient models for things, we're using the model for the waves that we use for the waves of the ocean to explain this quantum mechanics. That's all it means. It doesn't mean that it's a wave. It just means we are expressing this thing that we don't know what it is in terms of wave mathematics. So when you say you believe in the physicality of the waves and the collapse of the wave function, that makes you the only person in the world because the rest of us know that this is not a physical real thing. It's a mathematical expression of some real thing that we don't know what it is.
But some mathematics is missing.
So, hey everybody, and yeah, just a little a procedural thing. I'm going to have to leave the room because my refrigerator guy is finally here. Please do carry on, and I'll be back if I can. Shamash, Sam, Andy, Ben, if he comes back, shut the room down if it ends, and I'll see you guys later.
See you, John.
Thank you,
Sam,
John.
I've
See ya.
never heard you
Bye,
refer
John.
to quantum mechanics